So, good day everyone. I am Russel Monte from BSCE-1B. So, hi everyone. So, welcome to today's session where we will explore the world of trigonometric functions and, trigonometric identities. So, along with the underlying principles, we will cover the key definitions, principles, and simplifications and proving trigonometric expressions. But before that, let us first um, see our objectives. So one of our objectives are is to understand the basics of trigonometry. Second is to master the key trigonometric identities. Third is to simplify and prove trigonometric equations. Then, before jumping to our main topic, let us discuss first what are the core principles of trigonometry. So in this discussion, first is the proportional relationships. So imagine in a right triangle, so the ratios of the sides are constant for a given angle, forming the basis of sine, cosine, and tangent. So later on during the discussion, we will be discussing what are those cosine, sine, and tangent. Second is the unit circle principle. So um, from the unit circle principle, radius is equal to 1 relates the angles coordinates. From cosine is equal to sine theta with the angles measuring from the positive x-axis. Third is the angle measurement. So in angle measurement, so angles are measured in degrees from 0 degrees to 360 degrees or up. And we can also convert it into radians from 0 to 2 pi radians. With 1 radians is equal to the one arc length equal to the radius. Lastly, this is the Pythagorean principle. So where we the identity like sine squared theta plus cosine squared theta is equal to 1 follows the Pythagorean theorem so on the unit circle. So those are just the simplest or some of the examples of the Pythagorean principle. So later on, we'll be further discussing those different identities. So next is, let us first define what is trigonometry. So trigonometry is a branch of mathematics that studies the relationships between the angles and sides of the triangles. So especially the right angle triangle. So the word originates from the Greek trigonon, which means triangle, and metron means to measure, meaning measuring triangles. So now let's move on to the next terms, which is the trigonometric function. So here is one of our main topics that will guide us on how we simplify and proving trigonometric expressions. So trigonometric functions are mathematically functions that relate the angles of a triangle to the ratios of its sides. They are fundamental tools in trigonometry and are primarily defined for right angle triangle and the unit circle. So these functions are used to model and solve problems involving angles, distances, and periodic behavior. So I have here the 6 basic trigonometric functions. So we have the sine, cosine, tangent, and the cosecant, which is the reverse for the sine, cosine, tangent. So for the sine, we have the reverse is the cosecant, the cosine is the secant, and the tangent is the cotangent. So here and sine, so opposite side opposite over the hypotenuse. So it represents the ratio of the side opposite of an angle to the hypotenuse in a right triangle. The cosine, it is the side adjacent over the hypotenuse. So this represents the ratio of the side adjacent to an angle to the hypotenuse. Third, it is the tangent, so opposite over the side adjacent. So it represents the ratio of the side opposite of an angle to the side adjacent to it. Next is the cosecant. So cosecant is hypotenuse over the side opposite. So it is more like the reciprocal for the sine. Second, it is the hypotenuse over the side adjacent. So same, it is the reciprocal for the cosine. And then lastly, it is the cotangent. So cotangent is side adjacent over the side opposite. So it is the reciprocal for the tangent. So now let's move on to the trigonometric identity. So what are trigonometric identities? So trigonometric identities are mathematical equations involving trigonometric functions that are are true for all valid values of the involved angle. So these ideas are essential tools or simplifying, transforming, and solving trigonometric expressions and equations. So mainly the trigonometric identity. So we'll be using that later for simplifying trigonometric equations or and proving also the trigonometric equations. So I have here the types of trigonometric identities. So these are just the basic types of trigonometric identities. Not I am what I'm presenting now. It is not all the types of trigonometric identities. There are still more types of trigonometric identities. So what I'm just showing to you now, it is more like the types of trigonometric identities. We have the quotient identities, reciprocal identities, Pythagorean identities, so co-functions identities, the even odd identities, and the half angle formulas or the half angle identities. So here in Pythagorean identity, so it is derived from the Pythagorean theorem. So they express relationships between sine, cosine, and other functions. So we have here sine squared theta plus cosine squared theta is equal to 1. 1 plus tan squared theta is equal to secant squared theta. Then 1 plus cotangent squared theta is equal to cosecant squared theta. So those are the examples for the Pythagorean identities. Let's move on to the reciprocal identity. So in reciprocal identity, so this define the reciprocal relationships between the functions. So just like for example, sine. So sine, the reciprocal identity for it is 1 over cosecant. For the cosine, it is 1 over secant. For the tangent, 1 over cotangent. Same as with their reciprocal identities. Just like for example, the cosecant theta is equal to the 1 over sine theta. Secant theta is equal to 1 over cosine theta. Then cotangent is equal to 1 over tangent theta. Now for the even odds identity, so it describes the symmetry or trigonometric function. So like for the even function, we have the cosine negative theta is equal to cosine theta, negative theta is equal to secant theta, and odd function sine negative theta is equal to negative sine theta, then tan negative theta is equal to negative tan theta. It's more like if the given it is positive, then the answer is also positive. If the given is negative, the answer is also negative. We have also the double angle, so identities so this relates the functions of 2 theta to function of theta. Okay, so from the co-functions, it is more like just the co-function identities. These are the trigonometric functions which are implemented or identified by the pi 2 minus the theta given. So now let's move on to the so one of our main topic, it is the simplifying trigonometric expression. Simplifying trigonometric expressions is the process of rewriting complex trigonometric expressions or equations in a simpler term or more manageable form without changing their value. So this often involves the use of trigonometric identities to combine terms, eliminate redundancies, or convert between equivalent expression. So I have here the techniques to show you or to share to you for simplifying trigonometric expression. So firstly is use the trigonometric identity. So earlier I have presented to you the different or the basics of trigonometric identities. It will be quite useful for it to simplifying trigonometric expressions. Second is factorization. So factor common terms or trigonometric functions to combine and reduce expressions. Third is converting to sine and cosine. So express all functions to cosine and sine. It will be more easier for it to simplify. Just for example, if the given equation is in tan or secant, you should always consider it to express it into sine and cosine functions in terms of cosine and to simplify. Fourth is the combined fraction. So use a common denominator to simplify fractional expression. So some equation doesn't really need to convert into sine and cosine. Some equations, it is also good to combine the fractions or to look for their common denominator in order for it to simplify them. Lastly, it is to rationalize the denominator. So eliminate trigonometric terms and the denominator by multiplying the conjugate. So I have here examples that will be showing to you, just to show to you the what are the difference between simplifying and proving. So number one example, simplify secant theta minus cosine theta. So as stated here, write secant theta as 1 over cosine theta. So earlier I stated that in order for us to easily simplify expressions, we use techniques. So one of those techniques is converting tangent or secant into sine or cosine. So here in this problem, so secant is being converted into 1 over cosine. So secant, it will now be 1 over cosine theta minus the cosine theta. So next thing that will be done, it is by finding the common denominator. Since their common denominator is cosine theta, then by using the common denominator, we will be having the 1 over cosine squared over cosine theta. Then since the top or the numerator, it is one of the example of the Pythagorean theorem, so later on I have prepared examples that using the Pythagorean theorems, we can manipulate it to another form of functions or identities. So 1 over cosine squared theta is equal to the manipulation of the cosine squared plus the sine squared theta is equal to 1. So 1 over cosine squared theta is equal to sine squared theta. So that is why sine squared theta over cosine theta, it is the answer. But some terms, it can also be answered as sine times tangent theta. For the second example, we have sine x times the cotangent x. So we write cotangent x as cosine x over sine x. So sine x cotangent x is equal to sine x over cosine x over sine x. So cotangent x, it has been converted into sine and cosine for it easier to simplify. So we have here to cancel the sine x. It can be cancelable. So sine x over sine x cancel. So the remaining is cosine x only. Now let's proceed to the next, which is the proving trigonometric expression. So what is trigonometric expression? So proving trigonometric expression, so it involves verifying that a given trigonometric equation or identity, it is true or valid values of the variable involved. So this process often used in algebraic manipulations and known trigonometric identities, so to demonstrate the equivalence of two sides of an equation. So I have here also techniques to share to you. So first technique is to simplify one side. So start with the more complex side and simplify it to match the other side. Second is to convert sine and cosine, same with the simplifying. Rewrite all functions in terms of sine and cosine to clarity. Third is use fundamental identities, apply Pythagorean reciprocal or quotient identities as needed. Fourth is factor and combine factor, common terms, and common denominators. And fifth, focus on one side. And sixth, we have check symmetry and periodicity, where use even odd properties and periodic characteristics and trigonometric functions. So I have here just a simple example, so to show to you what are the difference between simplifying and proving. So one thing can be more visible, the difference between them, it is proving has an equal sign in its equation, while in simplifying there's no equal sign. Okay? So, prove 1 over cosine squared theta over sine theta. So, we will start at the left hand side since it is more like the more complex than the right side. So, again, you use the Pythagorean identity. Sine theta is equal to sine squared theta rather is equal to 1 minus cosine squared theta. So, it will be now sine squared theta over sine theta. So, simplifying canceling the one sign, it can be cancelable because sine squared theta factorable by the 2, multiplying the 2 sine theta. So, this matches the right hand side. Hence, the identity is proven because the left side it is equal to sine theta and the right side is also equal to sine theta. So later on in my next video, I'll be giving you examples and we'll be solving, simplifying, and proving trigonometric expressions. We will be having the simplifying trigonometric equation. So we have the number one example is secant x over cosecant x. So as you can see, sine and cosine is not present in our problem or in our equation. So first they must convert this two into sine and cosine. So as we all know, secant x is equal to 1 over cosine x. Okay? And cosecant x is equal to 1 over sine x. So using the division property, 1 over cosine x divided by 1 over sine x. So the reciprocal form for this to make it multiply 1 over cosine x. This will be sine x over 1. So 1 times sine x is equal to sine x. And cosecant x times 1 is equal to cosine x. So sine x over cosine x is equivalent to tangent x. So this is the simplest form for this equation. Today we have our second example for the simplifying trigonometric equation. So we have sine x minus sine x times cosine squared x. So as you can see, we don't need to convert it to sine x and cosine. So it's because it's already in sine cosine format. All we need to do is look for the common factor if there is any. So as you can see, sine x is present here and sine x is also present here. So sine x is our common factor. So we put sine x outside of our equation. So it will be this, like this. So sine x divided by sine x is equal to 1. Minus sine x divided by sine x cosine squared x is equal to cosine squared x. So as you can see, we have here an identity. So 1 minus cosine squared x. So from the Pythagorean identity, so sine squared x plus cosine squared x is equal to 1. So by manipulating this equation, we can have the equal for the 1 minus cosine squared x. So by putting the cosine squared x in the different path, so this will be sine squared x is equal to 1. So changing the sign from positive, it will now be negative. So cosine squared x. So 1 minus cosine squared x is equal to sine squared x. So sine x times sine squared x. So as you can see, we don't have anything to do. It's because it is in the simplest form. We only need to do is multiply them. So sine x times sine squared x is equal to sine cube x. So sine cube x will be the simplest form for this equation, sine x minus sine x times cosine squared x. Now we are on our third example for the simplifying trigonometric equation. So we have here sine cube x plus sine x cosine squared x. So as you can see, it is in the sine and cosine format, so we don't need it to convert na. And all we need to do is look for the common factor. So as you can see, same as before on our number 2, example, we have the common factor of sine x also. So let be sine x outside of our equation. So sine x divided by the sine cube x is equal to sine squared x. Sine x cosine squared x divided by sine x is equal to cosine squared x. So as you can see, we have a Pythagorean identity. So sine squared x plus cosine squared x is equal to 1. Then sine x, so by multiplying, sine x times 1 is equal to sine x. So sine x will be our simplest form for this equation, sine cube x plus sine x times cos secant squared x. So we are now in our fourth example for the simplifying trigonometric equation. So I have here a little bit complicated or a little bit complex example for this trigonometric equation. So we have cosine x plus tan x times sine x. So we will be applying the technique. So converting all the terms into sine x. So this is already cosine x and this is sine x. So all we need to do is convert this tan x to sine and cosine x format. So we need to copy cosine x plus, so the converting of tan x to sine x and cosine is equal to sine x over cosine x. So times sine x. So all we need to do is multiply this to sine x times sine x. We have sine squared x over cos x. So only copy the cos x. So what we will gonna do next is to look for the common denominator. So if this is cosine x, then the denominator for this is also cosine x. So all we need to do is multiply both the equations or both the terms to cosine x. So cosine x times cosine x is equal to cosine squared x. Then cosine x divided by cosine x is equal to 1. Then 1 times sine squared x is equal to sine squared x. So only need to copy this, sine squared x. So since they are already in the same denominator, we only need to copy the same denominator for them, which is cosine squared x. So we have here a Pythagorean identity. So cosine squared x plus sine squared x, again, it is equal to 1. So our new equation now is 1 over cosine x. But we will not stop there. It's because 1 over cosine x is also a reverse for the secant x. So secant x will be the simplest form for this equation, cosine x plus tangent x times sine x. So now we are here in the next topic, which is proving trigonometric equation. So I have here an example. Sine x, we need to prove that sine x minus sine x times cosine squared x is equal to sine cube x. So in order for us to prove that, we need to calculate the other side to make it the same in the other side. So sine x minus sine x, cosine squared x. So as you can see, it is already in a sine and cosine form. So all we need to do is to look for their common factor. So we have sine x here and also we have sine x here. So the sine x will be their common factor. So sine x divided by sine x is equal to 1. Then sine x divided by sine x cosine squared x is equal to minus cosine squared x. So again, so this is part of the identity or the Pythagorean identity from the sine squared x plus cosine squared x is equal to 1 by manipulating the equation. Since it is minus cosine squared x, we sine squared x, we transfer the positive cosine squared x from the 1. So from positive, it will now be negative cosine squared x. So 1 minus cosine squared x is equal to sine squared x. So sine x is equal to sine squared x. So sine cube x, I'm just gonna put this, sine cube x. So sine x times sine squared x is equal to sine cube x. So we proved that the sine x minus sine x squared, sine x times cosine squared x is equal to sine cube x. And that's it. We are now on our second example for the proving trigonometric equation. So we have tan x times sine x plus cos x is equal to secant x. So we need to prove that this part of our equation, the tan x times sine x plus cos x, is equal to the secant x. So in order for that, we need to use the techniques. So one of the techniques is to convert all the terms on this side to sine and cosine format. So the only thing we need to convert is the tan x. So tan x is equal to sine x over cosine x. Then copy this times sine x plus cosine x is equal to secant x. So by multiplying this, sine x times sine x is equal to sine squared x over cos x. So plus cos x is equal to secant x. So the next thing we will do is to look for the common denominator for this terms in the left side. So cosine x is their common denominator. So we let multiply cosine x. Okay. So cosine x divided by cosine x is equal to 1. Then 1 times sine squared x is equal to sine squared x. Cosine x times cosine x, it will be multiplied since it is in the numerator. So it will be cosine squared x. So their common denominator is cos x is equal to secant x. So as we all know, secant squared x plus cosine squared x is equal to 1. Then it will now be 1 over cos secant x of the secant x. So as we all know, 1 over cosine x is also the identity for secant x. So we proved that this equation, tan x times sine x plus cos x is equal to secant x. We are now on our third example for the proving trigonometric equation. So we have a little bit complicated equation. So sine squared theta plus cosine squared theta plus tangent squared theta over 1 plus tangent squared theta is equal to cotangent squared theta. So all we need to do is to prove this part or this side and this side. It will be equal to this side. So as you can see, we already have an equation or the part or the term here, a part of the Pythagorean theorem, which is the sine squared theta plus cosine squared theta plus cot squared theta over 1 plus tan squared theta. So sine squared plus cos squared is already equal to 1. So our equation now is 1 plus cot squared theta over 1 plus tan squared theta. So here, we also have here identities. So as we all know, 1 plus cot squared theta. So 1 plus cot squared theta is equal to secant squared theta. Sorry. I mean, it is cosecant squared theta rather. And for here, 1 plus tan squared theta is equal to 1 plus tan squared theta is equal to secant squared theta. So by converting them, so cosine squared theta over secant squared theta. So as you can see, we cannot convert it right away. So all we need to do is convert them into sine and cosine format. So from cosine squared theta, you can have sine 1 over sine squared theta. And for the second, we have 1 over cosine squared theta. So by converting them, our new equation for now is 1 over sine squared theta over 1 over cosine squared theta. So 1 over sine squared theta over 1 over cosine squared theta from the division form. Sine squared theta divided by 1 over cosine squared theta. So reciprocal it to have a multiplication. So 1 sine squared theta, so times cosine squared theta over 1. So by multiplying, cosine squared times 1 is equal to cosine squared theta, and sine squared times 1 is equal to sine squared theta. So we have also here an identity. So cosine squared theta over sine squared theta is the same with cotangent squared theta. So if this equation is equal to cotangent squared theta, and then we prove that they are both symmetrical. That is also considered equal to cotangent squared theta, and here is equal to cotangent theta.